All right, we're back. Accidentally pressed the spot button. I'm just making sure that everything is working so that I record the audio. Unlike last week or 2 weeks ago. So yeah, next week will be our last Make It Move, or not next week, but next session rather. Will be our last Make It Move session. That's going to be week number 7. I think 7's a pretty good number. It's kind of overrated. It gets hate on for being prime, but in reality, you could divide 7 into a lot of different ways. You could use it for like those scale thingies. So we're gonna have 7 sessions. Today is our 6th. So let's talk about autonomous, the autonomous period. So I did talk about this in weeks number 1 and 2, I believe, as a sort of introductory to why we do code. It's because in every single game for, I guess it's been that way since 2014. It's always been in the first 15 seconds of the match, robots move autonomously. Unless it was 2019, in which case you could also have opted for driver control, except you couldn't see your robot, so you had to use vision systems and all that. But 15 seconds is the beginning period of the match, and unless Reefscapes does something wild to us, then generally speaking, you're going to have an autonomous period. So points during autonomous, this is what's important. Autonomous is important because points are usually worth more, usually double, or something along those lines. For example, a speaker in the note during auto is 5 points. Now you could get that total from amplifying, but that'd take a lot of effort. So instead, if you score during the teleoperated period, you only get 2 points for a note in the speaker when you could have gotten 5. You also get extra points for moving. So this year it was plus 2 points. Last year was plus 3. 2022 was plus 2. I'm not sure about 2020. I think that was plus 5 or something. It depends on the game, but if you at least move during auto and you go past a certain line, you get some free points, which is pretty nice. So most autonomouses, let me get this out of the way. Most autonomous routines with Swerve Drive use something called odometry. Now, the most simple of autos are like move forward a certain distance or for a certain time. But if you ever want to do any motion in the X and Y direction and you want to do it quickly, then, for example, would it be like if you want to go from this point to this point, from point A to point B? Normally, if you had to work with like turn, move, if I bring it back to the hour of code metaphor from last week, basically you would have some commands, some blocks of code that'd be like move forward a certain distance, turn 90 degrees, that type of stuff. If you only had those, which are the most simplest of autos, you would probably do something like this. You'd move forward up to here, you would turn 90 degrees, then you would move forward to B. However, what most teams can do, and because of the availability of libraries and all of that, what most teams are able to do is they're in fact able to go directly from A to B. Now you could just be like, okay, what about turning? Well, in Swerve Drive you don't turn. With Swerve Drive, you could program the wheels to essentially go directly from A to B, shifting essentially without having to turn or rotate. So that's pretty cool. And additionally, if there's, for example, if I go ahead and clear this, if, for example, you want to go to point A and B, what if there was, let's give this coordinates. Let's say that there's A is 0, 0, B is 1, 1. The units are in meters. What if there was, a box in the way? Like, for example, in 2024, in the Crescendo game, there was a stage in front of the driver station that had 3 trusses. It was supported by 3 trusses, and if you bonked into those trusses 1-1, it would probably stop your autonomous routine, but 2, it'd be quite painful. So what if this was one of those objects in the middle? Well, most teams are still able to basically code a path to swerve around it, kind of like that. So they would safely drive around the truss or whatever object was in the middle. And that's achievable because of something called odometry. Basically, what odometry does is it's essentially a system that tracks the position of robots using encoders and gyroscopes. So those are things that you should usually be able to find with the Swerve module. Swerve modules, the encoders obviously are built into the motors, and there's also absolute encoders that you can buy. Like, for example, with Rev, we use the 3-bore encoders. for the turning motors. So the robot's position is represented with three components. So obviously we're gonna assume that the robot is playing on a flat or relatively flat surface. Now there's never been terrain in FRC since for quite a long time. Most of the games have been played on a flat field. There were some objects, for example, in 2023, the charging station was a slight elevation. There's also a weird cable cable line that a lot of robots tripped over, but generally fields are pretty flat. And so therefore we use X and Y for position, and then we use theta for what's called heading. So if you've ever been on a ship, or like if you've ever flown a plane, or if you're ever the captain of a ship, I'm sure, I don't know if you guys were, but if you were a captain of a ship and you're in high school, then that's pretty impressive. You should put it on your resume. But basically, with stuff like navigating, when you're navigating the waters, you generally navigate using a heading. Airports do that all the time. The runways are named because of the direction they face in. So heading is basically the direction that you're in. It's usually measured either from 0 to 360 degrees, or what Rev uses, what the Rev Swerve library does, is that measures it in radians. So you got pi over 2 radians, pi radians, 3 pi over 2 radians for these cardinal directions. You obviously have your zero measurement, but this is, if you've ever taken high school pre-calculus, this should be very familiar to you. If not, just note that you start by facing in the 0 direction, and then after that you face in the 0 direction, and then if you turn 90 degrees, so if you go from, like, for example, facing due north and you turn facing due west, that's pi over 2. If you turn another 90 degrees, now you're facing due south, that's pi radians. Not, did I say degrees? Radians, pi radians. And if you turn again and you're facing due east, that's 3 pi over 2. And if you turn 90 degrees and you're back to north, you're facing at 0 heading. So X and Y, I hope you know what those are. Those are just the X and the Y axes. So pretty easy. I hope this is pretty easy to understand. So basically, these three measurements are used to estimate a robot's position. In odometry, there's a lot of math behind it, but all of the math, thankfully, because I've seen the math, like, there's been explanations of how the math of odometry works. It is very painful. So we are glad that there's libraries out there to handle odometry and handle the hard stuff. But the part that you contribute to is getting the robot to move in these locations and using the libraries. Again, code is all about using the resources you have to make things move. So think of a coordinate plane for odometry, and also think of this red little box, that's the robot, and this arrow. So if the robot ever turns, the arrow will turn with it as well. And it utilizes a thing called drive kinematics. So kinematics being the locations and the dimensions of the swerve modules. And in that way, the robot essentially knows where its wheels are without like cameras and nothing. If you feed it the kinematics, it'll know where its modules are, how big it is, and this makes odometry so much easier. Before we move on, are there any questions about what I explained so far? Okay, moving on. So let's talk about some code analysis. So if I go into the code channel, that is our GitHub once again. That will lead you directly to Robot Container, which is the file that we'll be analyzing this time around. So let's take a look at robot.container.java. So usually, when you make autos, if you do like serious hardcore stuff with autos, you would usually place them in a separate file. But this time, for simplicity's sake, so that I have all the things in one place, it's generally not custom to do this, but I put all the autos directly inside of Robot Container, just because, one, they're pretty simple to code, so I didn't have to like take a lot of line space, and also because, again, I just like having all of it in one place, and it's the easiest to use. Robot Container, the file knows where it is. So let's take a look at this piece of code. So there will be comments. those will be indicated by the grayed out text with the double slashes. Ignore those. Those came with the library, and I wasn't able to change them yet. So just ignore those. I will explain what each line does. So line 191. So if you go to line 191, you will notice it says public command get autonomous command. This is the code that is ran when the match first starts, when you hear the da-da-da-dun-da-dun. I think it's a da-da-da-dun-da-dun, like that tone. It's different in Vex and FRC, but when you hear that, that means it's autonomous. That part of the code is run. So public command get autonomous command is run, and that's because if you go to robot.java, it'll do that. It'll schedule that command. So on line 191, this code is run first. And then line 195 returns m_chooser.getSelected. You don't need to know much about what that actually means. I'll get to that later. But just note that this command right here is a command for autonomous. It's either the command for the speaker auto or the command for auto 1. So if you are wondering about the names, speaker auto, that was that 2-note auto. And then auto 1 was just a move forward auto. So that was in place before we got our shooter. We would just move forward and get those free 2 points. So that's line number 195. Then if we go into speaker auto, that is this chunk of code right here. I'll go over one by one what the code means. So in line 198, whenever you declare a public final command and you name the command, that is a command, and if you include it in the sendable chooser thing, or if you have it run under autonomous command, that's what will be ran during autonomous. So again, you are a command and your name is speaker auto. Okay. Lines 200 to 204 is what's called the trajectory config. So this came with the template, the RevSwerve template, and what it essentially does is it configures what's called the trajectory. So whenever you make a trajectory, it'll come with those settings. So what a trajectory is essentially is it's a path. It is a path that goes from point A to B, and if you want, so for example, if you have like A, and then you got B all the way up over here, and then you want, like, let's say you want to pass through certain points, this is the trajectory, or this is the path of the trajectory, but the trajectory also has a certain speed and a certain acceleration, and that's what's declared here. And this is just so you can more control the speed of the swerve drive. So I had to tone these. So initially, these were set to 3, but I toned them down to 1 so that the swerve drive would run more smoothly and less like uncontrollably, so I wouldn't crash into a bunch of things and like do weird stuff. And then finally, you include the kinematics right there as well. So all lines 200 and 204 does is it's settings for any path. It's like attributes for the path. So like, for example, if I were to give you instructions to go from point A to point B, pass through these points, you would probably ask me, how fast should I go? How fast should I accelerate? Where are my body parts? But that's what this line is for. These lines are coded for. So lines 207 to 214, this is the actual paths themselves. So the same goes with 216 and 221. But for 207 to 214, the way you create this sort of path from A to B is you first declare, it's called a trajectory, example trajectory, and then you follow it these lines, trajectory generator.create trajectory, and then you have an origin point here, and then you have a list. So you could put as many points as you want there. I put just 1. You need at least 1 point there. But if you want to go for a straight shot, you could just have a point in the middle, and then finally a new point at the end. And what this actually ends up allowing you to do is notice how the starting and the ending point have 3 parameters: 0, 0, and then this thing called new rotation 2D. However, the points inside have just 2 parameters. The reason why is because that third parameter is actually the rotation, the heading. So if you wanted to say turn all the way around, so what this would do is first, like, what this code in a vacuum would do was it would start you at 0, 0. It would take you to 1.40. So it would just move you forward 1.4 meters. However, if I wanted to say move 1.4 meters, but also, and this is the cool part, but also turn the other way. So start, like, for example, if I wanted to, like, start forward, if I wanted to move forward 1.4 meters, but also end facing the other direction, I could change this 0 to math.pi. And what that would end up doing is, as the robot moves forward, it would also spin around, gradually speaking, until once it reaches its endpoint, it'll also be at math.pi heading. So it would be facing in the opposite direction, the complete 180. That's really cool, and that's something you can do with Swerve Drive, because it's with Swerve Drive you could go in all sorts of rotations, you could go in translations, and you could also spin around. And this just combines both of those movements. But for this 2-no auto, I just went forward by 1.4 meters. So no need for the rotation stuff, but it is very useful. So lines 216 to 221 do the same thing, except I start at 1.4, 0, and I go back to 0, 0. So this is another neat part, is that once you reset the odometry, if you don't reset it again, it'll just continue to track your position relative to the 0, 0 that you set it to. So the starting point is actually 1.4 to 0, 0, not 0, 0 to 1.4 again, or 0 to negative 1.4. So this just reverses that thing. And notice the config. Notice the config in each of these. That just dictates, again, the speed and the maximum acceleration of that path. Any questions before I move on? Before I move on to the next section. All right, neat. Cool. I do have a chat. No. Nice. All right. Actually, not nice. Y'all should be asking more questions. Okay, anyways. Lines 223 to 225. This creates the rotation PID controller. So this controls the rotation of the robot. So again, if you recall, PIDs help smoothen out movements, make it more accurate, but also relatively speedy. So that's pretty nice. So this essentially is the PID controller for the turning. All right, lines 227 to 237 and lines 239 to 249. This turns the paths we created, the trajectories we made, into command. So if you notice, this trajectory, it was just a trajectory, right? It was just a path. It's not an actual instruction yet. It's just a path. So you can't really run a path, you can't run a trajectory, but you can run a swerve controller command, and that's what lines 227 to lines 237 make. So when you declare a swerve controller command, you feed in that example trajectory. So the path, you feed in this thing, which is basically, it's just included with a template. It's not really, it's kind of like an boilerplate, like a redundant thing, but it's needed. You import those kinematics, the dimensions and all of that. You put in the KPX and KPY. So these are the PID controllers in the X and Y direction. So movement, translational wise. So what that essentially does is it is the PID for moving. Translation, the lines 223 to line 225 was just the rotational PID controller. Lines 236 and 237 are they just feed in the subsystem that is going to be used. So when this is ran, so when this swerve controller command is ran, what's going to end up happening is the robot is going to move 1.4 meters forward because we turned that trajectory into a command. Same thing goes with lines 239 to 249. Notice how I use the same PID controller, the same theta controller, the same subsystem, and the same pose and kinematics, but I replaced the trajectory with, instead of example trajectory, which was this thing right here, I replaced it with second trajectory, which is down there. So what this would end up doing is rather than move the robot forward again, 1.4 meters, it would move it backwards. It would take it back 1.4 meters, returning back to its starting location. So now we have the two movement commands. So you might be wondering, well, Autonomous isn't just moving, right? You still have to intake the nodes. You have to shoot him. You got to you got to move around as well, but you have to intake, pivot, all of that, right? How does that work? How do we fit those in? Well, here's where we do this thing. So, first of all, lines 232, it resets the odometry so that it sets the robot's position to 0, 0, 0. So 0x, 0 in the y direction, the coordinates are 0, 0, and it's facing in the 0 heading. So that means that no matter where it starts, it'll know where to go. This is where the magic happens. This is the kind of sandwich meat, the main course of the code. I don't know. I think this is like the sandwich, and everything else is like the recipe for the different ingredients above. So this function called sequential command group, what this ends up doing is you could put as many commands within these parentheses, and what it'll end up doing is it'll run the first command, then the second command, then the third one, the fourth one, the fifth one, the sixth, and it'll go all the way down until the end. So let me just go ahead and let you guys know what these are. The first one, this is a wait command, so you know it's going to wait for 2 seconds. This was because in one of our matches, the other team wanted to shoot first, so we'd wait for 2 seconds and then shoot. Line 258, what this does is it's the pivot PID. I think I've showed you guys before how the pivot PID worked, but it would pivot up, and then it would pivot to the speaker set point. Afterwards, line 259, that'll start rotating the motor, so that'll eject the note and shoot it into the speaker. And then 260 is a wait command for half a second. And the reason why we use this wait command is because we want to wait half a second for the note to fully exit the shooter before we turn the motors off. Because whenever you run this command, it just sets the speaker's motors to full power, and it'll just leave it like that until you stop the motors. So it'll just wait half a second, and then it'll go to line 261 and then stop the shooter. Afterwards, it'd pivot down, and then it would basically line 263 and 264. Those would start spinning the intake in and also spin the shooter backwards. So if the note were ever to come into contact, it would get sucked in. Lines 265, finally, this is our movement. If you recall, that's swerve controller command. That will move our robot forward by 1.4 meters. Then it'll wait for 1 second, because it'll move forward 1.4 meters, and then it has to wait before it does anything else. And then it'll stop the intake and shooter. By this point, the node should already be inside. It'll move backwards by 1.4 meters. It'd wait for 0.75 seconds. It would pivot upwards. It would eject the note. It would wait half a second, pivot downwards, and then stop everything, getting ready for the teleoperated period. So that's that. It's not actually a lot. It's just like as long as you could break it down step by step by step. Like it's kind of like making a peanut butter and jelly sandwich, but except you move as well. So like you don't just say get the bread out, put the peanut butter and jelly on, and you close it, and you have a delicious peanut butter and jelly sandwich. Again, with stuff like this, you have to kind of break it down. You got to say, okay, well, you're in the kitchen now. You got to move forward, turn left. You'd be in the pantry. And then you would reach up to the third shelf, get the bread out. Reach to the fourth shelf, get the peanut butter and the jelly out. Grab all of that. Walk out of the pantry. Go, find your nearest table. Lay the bread down. Open up the peanut butter and jelly jars. Get your butter knife or whatever knife you use. Dip it in, spread it, and then you have to kind of break it down. And when you break it down, this doesn't look like all that much, and this is really pretty simple. However, I will take a look at the modifications we did have to use to get this auto to work. All right, any questions before we move on? Okay, let's move on. So I did have to make this new command. So if you recall, in our commands folder, we have pivotpid.java. So this is the code for the pivot. This would basically be the code that raises and lowers the pivot and shoots the node in. However, you might have noticed auto pivot PID.java. Now, this is very similar to pivot PID.java, except we only run this command in Autonomous. And here's why. If you schedule a command, if you have a command out, if you schedule it, and it's, for example, like if it's a PID command, PID commands by default run for indefinitely long. They run until something else happens in the subsystem. So in the case of the pivot, the PID, if you think about it, so if you have like a pivot, and this is like the shooter mechanism, right? It would take the nodes and take the nodes out. And here's the pivot. If you were to run a pivot PID instance, it would pivot up. But what will happen is that the motor will keep on making those calculations, ensuring that it's always on the dot, accurate. It'll just keep on running over it, like it will keep running forever and ever. So if this, for example, if I replace this auto pivot PID with just a pivot PID, it'll pivot upward and it'll just stay there. It will just keep running and running and running. It won't move on to the next command. So that's what auto pivot PID does. Or auto pivot PID mitigates this issue during Autonomous by adding this thing called a timer. When you have a timer inside and you start the timer, so line 25 says, okay, there's a timer. Line 34 says, okay, we're going to initialize this timer. So if you have a timer, it's not going to immediately start counting down, right? So you got to go to line 41 and then start the timer. And so what the timer does is it just basically counts the number of seconds since it's been started. And if you notice in lines number 58 to 62, there's this function called isFinished. So what isFinished does is it returns if the command is done and we're ready to move on. And this line of code, line 59, basically says, okay, if the timer has been running for longer than 2 seconds, it's true. The code is done. isFinished would return true, which would signify that, okay, it's time to move on. Otherwise, it's false. And isFinished, I believe, actually does run 50 times a second as well. It runs continuously, and once it finds out that the timer has exceeded 2 seconds, it just stops the code. And that actually works really nicely. So here's what happens. This is basically it's the IRL simulation, but actually not really, because we don't live in a simulation, hopefully. If we do, I'd be very disappointed. This is basically the result of lines 256 to lines 278. This is what you get. So, okay, I'm going to have to turn the pen off. So if you notice, we're about to run it. I count down. And then if you notice, it pivots upward. Okay, and it waits, or it pivots upward, and then afterwards, it ejects, so it runs the motors. It waits half a second before pivoting downward, because if we pivot it downward immediately, then the note might just go, it'll not go in the hole or in the speaker, it would just fly all over the place. And then it pivots downward, and then it moves forward, and notice that it also spins the intake and the shooter inwards, so the note gets just pulled in. And then it goes back, pivots upward, and then shooter goes in. And in this case, since I think the code cut off at 15 seconds, so the shooter kept on running, but you could disable that with the controls in Teleyop, unless they're disconnected, in which case, that's very unfortunate, guys. But yeah, that's the 2-note auto. That's 12 points right there. 12 points is already very good. I think that was like the average EPA. So if you get 12 points and you get a bunch of other things during the match, pretty good. All right, let's talk about the sendable chooser thing that I've been alluding to this whole time. So, a sendable chooser, what it essentially does is, I don't have a photo of it right now, but what it essentially does is, if you go in the dash shuffleboard, the shuffleboard, not the dashboard, the shuffleboard, if you go inside of that, with the sendable chooser active, it'll essentially have a square, like a module that has a drop-down menu. And so before the match starts, while you're turning the computer on, once the code has run, or started to run, it'll have a drop-down menu. And basically what you would do is you could click on it, and then you'd be given a bunch of choices, and based off of the choice that you picked, it'll run that specific autonomous mode. So this is all in robotcontainer.java, and this is all the code related to sendable chooser. So if you go to line 86, this declares that the fact that the sendable chooser does exist, and it contains inside of it commands. So if you see these two arrow brackets, this signifies what type of data will be contained in this sendable chooser object. Lines 114 and 115 essentially add options to the sendable chooser. So the default option was actually the move forward auto, because if in case something went haywire, I didn't want to to risk anything going wrong, but we did use a speaker auto multiple times. That was the auto that was in this video. So whenever you have this set default option, you add an option. This just goes to the drop-down menu and adds those choices in. This first parameter is what it will be called on the shuffleboard. So it's a more user-friendly name. And this parameter afterward is the specific command that'll be run. So this auto1 refers to this autonomous command right here. And then speaker auto is, of course, the stuff I just went over about 5 to 10 minutes ago. And then finally, once all of that's done, we put all of that data on the smart dashboard, in this case it's the shuffleboard. We put all of this on, and so once the code is ran, the driver will see the drop-down menu in all its glory and be able to select from it. So pretty useful. If you don't want to go back and upload code, you could just use a drop-down menu. It's very nice. Very nice. Any questions about this? About sendable choosers? Well, believe it or not, my friends. Yes? Pranay? Alright. Well, believe it or not, that is it for this week. There's not really anything y'all could do for autonomous because, one, y'all don't have a robot. So there's not really much to do. I'm fine. I'm glad you're fine, Min. Alright, yeah, so there's not really much to do. I just put a smiley face here. But do note, we won't have a session on July 12th, because I won't be available. So our final session, Make It Move, is going to be on July 19th. It'll be our last session. So, enjoy it while you can. Have a great rest of the summer. Are there any questions, comments, concerns, grievances, qualms about anything we've done today? Cool. If that's the case, have a great rest of the week. Have a great next week, and have a great first 5 days of the week afterward. And I'll see you in 2 weeks. Thank you.